I'm coming, I suppose, live from the laboratory in Pats, and you can see it's very like a school lab. It's so this lab was built in 1967, but there's been a lab here since the 1890s. So this was the new lab in 1967. I don't quite remember it, that year, I mean, not quite, but I am a kid of the 60s, okay? So I'm the only one qualified to say the word groovy. That's just have to take that as such, you know. You're all too young to know what groovy means. So there's a few things we're going to do this morning. We're going to, well, we're going to do some microbiology. So while I'm sort of talking and showing you around, if you wouldn't mind in the chat, it's just maybe describing what microbiology did you do as a Leaving Cert student, okay? I'm guessing you did something, okay? So I'm going to take you around and show you a couple of things that we're going to do this morning, okay? So you put that in the chat. What did you do? All right. I'm really jealous when I see people drinking coffee this morning. Being in the lab, of course, I can't even take a sip of water, you know. It's like it's like a graveyard here. There's not a single person around, you know. So it's fairly spooky. Had to set up everything myself this morning. So it was like being back in school. You know, you got to do all your own prep and all your own setup and so on. So station number 1 here, what do we got? So you can see I've got a Bunsen going there, all right, on yellow flame. Now it's a freestanding Bunsen. It's not a tubed one that you put into the tap. We switched over to these some years ago, okay, because it was going to be cheaper than replacing all of the pipes. In microbiology, we use things like these are nichrome wire loops, but these are the ones where we have the wire and we put them into make our own loops. Okay, they last for years. And then the other thing will be what we use the Bunsen for. We use the Bunsen to flame the loops, but we need to make some spreaders. So I'll be showing you how to do that with some glass rod. So we have nice new glass rod there, and we'll be doing that. The other thing we need here, of course, scissors to cut the wire, or pliers or something like that. So that's station number 1. Okay, so station number 2. This is our laminar flow. Now, the school I worked in, we had been given one of these. Okay, so I'll talk about that. What you do when you don't have one, which is what most schools wouldn't have. Okay, but as I say, in Ashburn Community School, which is where I was teaching last, we got given one of these. So wow, all right. So what have I got here? Well, I've got some bacteria. Okay, aren't you glad not to be here? I've got some bacteria bought in. Okay, that's the school supplier. I have a couple of old samples of bacteriophage. Okay, if you know what phage is, Phage. All right, if you know what that is. I've got an assortment of leaves that I've collected outside here on the campus this morning. I have a hole puncher because that's going to cut me some little discs. And also what I've got are these things, which are antibiotic test discs. So we're going to be doing a little bit on that as well. All right. So we got lots to going on here. I always have a little container of Milton fluid, not because any babies need their nappies changed, but but more just because when I'm finished with things, I'm either going to reflame it in order to sterilize it again, or else I'm going to dunk it into the molten fluid. Now, I just mentioned back there nichrome wire loops, okay? And if you're not using those, then you're buying in these horrible little plastic things, single-use plastics, yeah? So the old single-use plastics, I'm trying to get away from that, okay? So I'm going old school, and in old school, you have to use a reusable thing, all right? Hence the metal, okay? So that's station number 2. Now, station number 3 is here. And can we see that? Yeah. So this is our giant autoclave. Now that's a giant in terms of school. And that's, so basically what an autoclave is, it's a pressure cooker. Okay. So this happens to be one that we're going to be putting our Petri dishes in. Okay. And these are our Petri dishes. And you mightn't have seen these before because these are glass ones. Okay. You can use the buy-in again, the pre-sterilized plastic ones. The ones that I use, because I come from a school background, are glass ones, and I can reuse those. So some of these are maybe 40, 50 years old. Okay. We get no prizes for guessing who invented the Petri dish. Now, station number 4 is where we have our agar preparation area. Okay, so we've got our weighing scales here. Okay, this is better than what we need. We've got our stirrer hot plates. Very important to have the stir and the hot plate. We have conical flasks, and we've got some tubes. Usually I make up the agar in flasks, and then I might have a set of tubes where I pour the agars out individually for all the students to have their own individual tube, and then they just pour it into the plate, give it a swish around, and then let it harden. Okay, I mightn't do that today. I might just keep it in the flask, but I'm just telling you what I would do when we have students in classroom. Now, okay, what have I got in here? Right, well, so again, you can also buy in agar plates ready made up, okay? So that's if you're in a well-off school and they don't mind buying in that kind of thing. You can also have the agar, all you need made up dry. So you just add water, okay? Get it up to about 97 degrees. And then the other option is to make your own agar, where you buy the agar flakes, you add the sugar, and depending on which one you're making, is it a beef one or a yeast one, you use either Marmite or Bovril. Okay, so yeah, supermarket. Okay, so that's really easy. This is the stuff they don't teach you in when you're studying in college. It's like they never teach you how to actually, what if you ran out? What if the stuff was off? What if it never said it? What can you do? Because you've always got a lead time of several weeks if you order from the science supplier and you order this in, because I've just realized I'm not going to have any agar. What can I do? You've got everything else ready to go, and it will happen. It will happen that you will come upon a time where you've got everything in place and you've just gone, dang, I forgot to order new agar. Okay. What are you going to do? You're going to cancel all your practical? You shouldn't do that. Okay. What you can do is in lunchtime, go up to the health shop or the supermarket, and you can get a few ingredients and you can get it. So we'll teach you that today. Was there another station? Well, that's a big one. Okay. So first thing where we could do this at the moment, because I want to get a bit of solutions made. I just ran off screen. Yeah, that'll happen sometimes. I tend to run around the place. Okay, so, and the other thing I never do without my instructions. That's the key thing. So I never, even after all these years, I always like to have just a bullet point set of instructions, just which one it's going to do here. I'm going to make up starch agar, and the reason I'm doing the starch one, it's one of the mandatory experiments. I know I've got no head now, but sure, it's not much to look at. The starch agar, can you think about what experiment that is? Anybody put that in the chat? No? You telling me you don't know? Well, what you're doing is you have to think about what an agar is, right? Okay, it's a medium. Fair enough. It's got certain nutrients that you want to demonstrate its breakdown. Okay, it's a catabolist, and that's done by whatever you put on it. So we might put seeds, for example, on starch agar, and the enzymes from the seeds will actually leach out into the agar and digest the starch. Fair enough. Okay, and then what we can do is we can then test the plate for the whatever starch is on it. And what we should find, here's hoping, is that there are areas where the starch has been hydrolyzed. Okay, that's the theory anyway. You know, there's always a bit of theory. You know, the theory is it going to work? Okay, so we're using spatula. You know, there's two types of spatula. Here's a third one. You know, does it matter? No, it's fine. Okay, so we're just gonna measure out a gram of starch, as I recall, 1.5 grams of agar. And it's not critical, you know. It's not exactly, it's not bucket chemistry, but it's not going to change your life if you get it wrong or whatever. So, excuse me. Here's some just some neat agar in here. This is why I need a long spatula for this guy. And we're just going to add, take that out of there. I'm going to put in 1.5 of the agar. Well, I know it's not going to be that much. It's going to take a while to get up there. That's only 0.5 gram, Tom. Didn't think I was going to get there. Okay, right. We got so we pop that in there. Pop. These are old, and they're just polystyrene, and they high density polystyrene, and they crack the minute you bend them. So I'm not going to worry too much there. Just get me no, we just want about 100 mils. So this is if I'm just making a small number of plates. Okay. So yep, that's it. Okay, so what you do is, to start off with, don't just pile all of the water in, because I know this is like cookery demonstration, but there's a good reason for that. If you pile all the water in, it just goes lumpy. So we just get a sort of a pasty water. We add our magnetic follower. Okay, magnetic follower. We add that in there. Now, the hot plates, get one with a stirrer. Save yourself a lot of problems. Okay. So we get that going. We get the heat. This one you can set the heat on, which is far better. Please don't be putting them on Bunsen burners on tripods and gauzes and all that nonsense. Just don't do that. Okay. You know, somebody somewhere, they're going to have some kind of a hot plate or a water bath, you know, either. So this is the rest of the 100. So we're going to make that up there. Just now we can add that. So basically it won't dissolve until it's near boiling. Okay, so that's how you do it so that you don't get lumps or you'll be all day at it. So that's number one. We're good. We're starch. So that's that one done. I'll show you how to make the homemade one. Okay, so the homemade one. Okay, slightly different. Where's that? So I'm using sodium chloride. Now I'm using the chemical sodium chloride. I'm not using table salt. Would it matter? Could I use table salt? Sure, yeah, of course it would be fine. You know, life's too short, lads. You know. So we're only looking for 1/2 gram. The issue with using table salt will not give you, if you were doing, say you get roped into doing leaving cert chemistry, lads. Do you know what? You'll get asked to do all sorts of stuff when you're a teacher. Say you're asked to do leaving cert chemistry, it will mess up calculations because you've got other things in there. Okay. So we start off, we just need, and I'll put these recipes, if they're not already on Loop, though we all know how great Loop is at the moment. Sure, look it. Okay, so that's 1/2 gram of salt. Oh, we're back to this crack again. Let's see, can I type it out, as we say in Fermanagh? A little bit too much there, Tom. Yeah, that'll do. There's our agar. Okay, and then, and this is the great crack, you've either got a choice of beef or yeast extract, and I usually go yeast extract. Okay, so, wow, that's great stuff. Better to nearly get up to have it's very icky sticky. Now we want to try and get this onto a weigh boat so I can actually get the right quantity. So there's a little bit of fustron, as we call it. You might know what I mean by that, fustron. So I'm just looking for a couple of grams of this. Yeah, that's what I figured. That was way too much. Okay, so again, we could buy in everything there. That's enough. That's about 2 grams. Pop that in there, down the bottom. We measure our 100, same thing as before, 100 mils of water in a cylinder. Yeah. We add a little bit just to start ourselves off here. And the other thing we do that's a little bit different, just start off with a bit of heat because we want the yeast extract, because it's really gelatinous, to get into that. You can see now, so it's starting to, there you go. Now nothing here, we're not doing aseptic technique at this stage. We'll get to that after a while. when I'm teaching Leaving Cert biology, I also taught Leaving Cert chemistry. I always got the students to wear proper lab coats. It was just one of those things. It's just, you know, it worked for them. So that was salt, agar, yeast extract, water, has a little bit of water. I add a magnetic follower. And I'm putting the heat up to 97. I'm starting to do that. I need to wash off the yeast extract off the spoon, of course. Only it was that easy. We're going to rub the spatulas to try and hoof off the. So that was a very rough estimate of about 2 grams, okay? So there we go. So we're ready to go on 2 agars. And we add the rest of our water that we need there. Okay. All right. Now, and then the third one, just for the crack, was malt extract. Now, the other thing that as a teacher, I've always found useful is having a multi-tool. Well, when I was a teacher, it was a Swiss Army knife. And just having, yeah, I know, jokes by being from the north and always carrying a knife, you know, and all that jazz. But yeah, really. But I always carry a knife. Yeah, it's true. What can I say? So we're just using 2 grams of this in water, just as before. Yeah. Okay. Of course, I love Marmite, so resist the temptation to lick the spatula. I better wash it. Okay. So we need 2 grams. We make sure that the spatula is really clean. And we just need 2 grams here. It's the easiest one of the whole lot is when you buy in the agar. It's quite expensive to do. It's the only thing. Okay, so there you go. It's already made. And we pop it in there. Okay. Same again on the water front. I don't actually have a still here. I just use deionized water. I think for school chemistry, that's fine. It'll tell you different times distilled water. I never found it made a difference to anything I ever did. So I've never had an issue with that. Whereas, you know, if you have a still, you know, who's going to maintain it? You know, the darn thing breaks down. What are you going to do? So that is an issue. So third one, get the water in there now. That's the easiest one of the whole lot. Okay. Noisy. Again, get it up to, so we'll just turn that down. And what you see here, guys, messy, messy, messy. Kind of obvious which one's which. I hope it is for you. Okay, so we got 3 agars. So we're just going to let that. I don't want it really necessarily to boil. It's 97's fine. Okay. Certainly don't want it to boil over. Okay, So you let that, so you clean the knife. An all metal one's good because you can sterilize it when you need to. So I'm closing up everything now. Make sure we don't get dust in here. You know, in this room, there's a lot of an old building. The building's 1889, even though the lab is 1967. So there's always dust coming down. We don't want to get that into any of our Agars. Okay, so we're at number 2. Well, I think it was 1 actually originally. Okay, and we can do this sitting down. All right. Okay, so just to remind you, because it's so you might be out of practice. Okay, how to use a Bunsen. Okay, now what makes a Bunsen different from any other gas burner is the collar. Is this thing that rotates. That's what makes it a Bunsen burner as opposed to any other sort. Okay, now turn on the gas, light it. When the collar is closed, you get a yellow flame. That helps you see what you're doing. Okay, if the light is shining in through a window, you won't see a blue flame. People will burn stuff. It's not good. Okay, so we're gonna just make a loop with nichrome wire. Nichrome is nickel chromium. So, and that's a nichrome wire holder. It has a little screw end. So we can just pop it in there like that and then tighten it. It's going to work, is it, Tom? And there we go. It's just gone a little bit iffy. That's it. So the wire's held in there. And then, of course, what we want to do is just put in a loop. Now we can put in a substantial loop and then tie that. We can. So that you end up literally, I don't know, can you see that? No, against white. Okay, so it's just a little loop of nichrome wire. All right. Now, when you're sterilizing it, you put onto blue flame, and you get it so that until it's red hot. I don't know. Can you see that with your thing there? Okay. So that's that. Now, the other thing I want to do is make a spreader. And basically what it will look like is, I don't know, just like a bent piece of glass, I suppose. So what I'm doing now is I got the glass. This is solid glass rod. We need it to about the top of the blue flame, which is about there. I'm going to make it a bit smaller. If I hold it there, you get a yellow flame when the glass is getting hot enough. And you rotate it so that the full thickness of the glass gets the full heat. So maybe you did all this before. Yes? No? Anybody? I'm thinking no. So I don't know, can you see there's a yellow flame now on the glass? I'm rotating it. And now I'm just pulling it down slightly. And I'm putting it there to about, it looks like about 45 degrees. Okay, you don't put it in water because it would shatter at that. Okay, and then I'm just going to put a little bend here. That's very hot, so I'm not going to hold that. So the hottest part of the flame is always at the very top of it. Bunsen flame gets to in and around about 1,000 degrees centigrade, but only at the top. Okay, so that's just to give you a little piece of glass that shape. Now it's way too long, of course. Oh, out comes the, and this time on, you either have a file, a little, or a glass cutter or something like that. I have a file, and I'm just going to cut that. Just put a little notch in it. Don't burn myself. I can turn off the, no, I will use the Bunsen later. Now, just looking over here now at the lamp flow. Now what this is it's a large unit, and it brings the air in at a horizontal, hence laminar flow. Okay, and it then has lots of filters, high grade filters up here. So all of the bacteria that might come off something are in there. You don't need a Bunsen to, if you don't have a laminar flow, what you do is you have a Bunsen working on a table, and it creates an air current, and that means that any bacteria in the vicinity is drawn up into the air current away from you, okay, away from your plates actually, which is what you're trying to do. Okay, so you wouldn't use these together because they do supposed to do the same job, but I'm going to be using the Bunsen to flame my loop. These ones are sterilized already, but we still have to sterilize. At least that one was when the door was open. Okay. Yeah. So these are sterile. You can buy them cheaper, not sterile, but then you can't. What good are they? So they'll tell you on them they're sterile. That's important to make sure. Once the packet's open, they're not sterile anymore, and you'll get other things growing in it. So, well, why did somebody just leave a packet like that? Because in biology we use petri dishes for every darn thing. So we use them for a lot of stuff. So agars are nearly ready. So we have, I don't put those will melt in the autoclave. They're sterile, they don't go in. These do go in because they're glass. And then the 3 agars. Now, that's fair enough. Now, this is not just any ordinary cotton wool you get in the supermarket. This is microbiological cotton wool. The reason is if you use ordinary cotton wool for this, what happens is that it just gets it absorbs your agar, and then it ends up going down into the agar, and you've got to fish it out. Well, that could happen anyway. But sure, look at here we are. So we put a plug of that on. So I'm kind of guessing that. So there we go. There's that one. It's that one. I can get the follower right afterwards. Doesn't matter. There's that one. That thing. That's our Petri dish stack then. That goes in. Okay, now when you're sterilizing, all right. So basically, it's a pressure cooker. All right. We got our 3 Agars. We got our Petri dishes there. Okay. Now, it's basically you've got a bucket in there. It's got holes in it. You add enough water. Okay. Fill the bottom. Yeah. Looks like it's got enough. All right. We close it, and then we start that. Okay. And that's how that works. So that can take a good bit of time. So we let that run, and then we've got other things that we can do. We're going to pour some plates, and then we're going to inoculate it with this is E. coli. Okay. Now these are the K12 and the B2 strain. Somebody is just entering the waiting room, so we'll let whoever that is in. I presume they're human. So you can see that that's E. coli, the B strain, and E. coli, the K12 strain. They're relatively safe. What you would not do is use any other strain of E. coli. It would be far too dangerous in a school context. Okay, so that's important. Okay, now I just happen to have some old then. I was telling you phage solutions. Okay, and there are 2 strains of phage. And what we're going to do is to do a little experiment. All right, so that's instead of just merely, you know, we could just grow some bacteria on agar plates to demonstrate, you know, agar growing, you know, big deal, or rather bacteria growing. I don't think that's a huge, you know, there's anything to learn from that. Okay. However, talking about phages, bacteriophages, they are the viruses that kill bacteria. Okay, it opens up a possibility of getting into science and technology and society, a discussion on that. So for example, all right, where do you find phages normally? And typically you find it in raw water. Okay, streams, rivers, ponds, soil, sewage, and so on. You find it in raw, untreated materials. Okay, and what's happening is they're usually viruses don't feed because they're not alive. They just replicate. Okay, and what these bacteriophages do, or phages do, is that they replicate in the bacteria that are in all of those things. So the more bacteria in those waters, the more phages that you will find. Okay, so if you've got water and it's contaminated, okay, you're going to have more phages in it. Even if you don't find the, say you don't find the E. coli in the water, if you can, there are ways to filter water and then actually then to filter out the bacteriophages and do a count, actually count and estimate of the amount of bacteriophage, and that gives you then an indication of how clean water is. Okay, now people are very slow to take on to do this. This was something that I would have worked on in the 1980s. All right, and it really still hasn't been kind of taken on as a thing. Okay, now the other thing we're going to do with these guys, we're going to work out which antibiotic they don't like. Okay. Now, not all antibiotics do the same thing. Okay. We've got two main kinds here. Okay. These are the gram-negative so-called antibiotics, and these are the gram-positive so-called. And that's two main classes of bacteria, gram-positive and gram-negative. And that's to do with a stain that when you're first identifying bacteria, you give them this staining procedure, and it identifies them either in one big group or the other. Okay, because and I've forgotten which is which, but one of those groups, okay, the bacteria tend to be much nastier than the other one. But okay, so we're going to see is E. coli gram positive, gram negative, but also which of the antibiotics are effective against these strains of E. coli. And remember, I've already said they're not particularly rough. Now, so those two experiments, they're what I call ancillary experiments. You should do them in order to get into discussions with the children about the role of antibiotics. And it also, this is the only school experiment, the one with the viruses, that you can do with viruses. There aren't any other experiments that you can do in secondary school on viruses. Okay. Now, mandatory experiment, when the starch agar comes out, it's going to be, we're going to look at the natural fungi that grow on leaves. And this is the perfect time of year to do that. Okay. So there's type number 1. Okay. Type number 1. Okay. Now, you don't need to know then this leaf, because I'm probably guessing that most of you can't identify. So prove me wrong in the chat. Let's see, can anyone identify that leaf there? It's got jagged edges. It's got red portions on it. It produces red berries from cream flowers. It's has a strong scent of almond. And what I'm going to do is I'm going to make little perfectly shaped discs of the leaf that I can put in the agar plate. So that's type number 1. Okay, so I got 4 little discs. Anybody? No? Oh, sad. Okay, so type 1 equals rowan or mountain ash. I wasn't asking for the Latin name, you know. Okay, so I might then keep that and dry it, and we can then put it. Type number 2. Any thoughts? Go no. Just tell me no if you haven't a clue. Anybody? No. Well, I'll tell you. I'm cheating because it's nope. Okay. This is actually holly, but it's only got one point prick at the end. It's a garden variety. 4 little discs. Okay, that's type 2. I put them in order so I know which is which. Type 3 is falling to pieces. Okay, that was attached as a leaflet, I think there. Type 3, it's an ash. Now it's golden ash. It's not our native ash. Okay, so type 4. Any thoughts? If you said maple, I'd give you it. All right, it is a maple. It's type 4. It happens to be Cappadocian maple. Anybody know where Cappadocia is? No. Turkey. And then last one is a fairly scrappy looking leaf, 2 leaves here. You can hear the way that it sounds, feels rough, and it's got the jagged edges are very distinctive for this species, and that is elm. But it's a garden species, it's not native. Mils. This is useful also when you're a teacher. 100 mils of agar will make up 5 petri dishes. Okay, so they're all liquid. So just leave those to one side. It's better to leave them all individually flat so that the surface of the agar is in contact with cold steel. Nutrient agar. Now we've got, if you remember, this is using the marmite. I think it was marmite. I didn't use beef extract overall. It's marmite, this one. So open the bag, rip it open, but don't take them out. One at a time. Now upside down, flick. Then open. The leaf, putting the leaf discs so that's the leaf discs on the lids, and that goes over the agar. Okay, so and then what I forgot to turn on the thing, so what you see here are different species of seeds. What we're doing here is we're testing and control. We're testing the viability of those seeds. I don't feel any germination actually. So I don't need to do huge number of replicates. So you have to leave them. Right. So you don't need the Vaseline anymore. What we do now just, as I've done here, we've got our seed assay, we've got our antibiotic assay, so that's our 4 practical. One day all of biology. You could decide to do 1 or 2 of those. You could decide to do 1 or 2 of those in 5th year, or 2 of them in 6th year. So you could spread it out. You could decide to spend. You could also do 1 of them, for example, not the mandatory one if it's required in the Leaving Cert, but you could certainly do 1 of them. I used to do microbiology in transition year, and I would do the phage in transition year. So there's definitely, okay. And just to then recap, mandatory experiments doesn't mean they're the ones you only do because you have to do them. They're the minimum. Everything else you to add on. Why do we do the ones with the phage? Because it's the only one you can do in school involving a virus, where this is about the assay of the antibiotics, about discussion of the role of antibiotics in antibiotic resistant bugs. You've got then leaf molds. That leads into ecology, so it does. And then you've got seed assay on starch plates. Again, that's ecology. So the seed assay is actually to determine whether the seeds are viable after being in storage here in our herbarium facilities. So these are actually seeds that were collected in Greece, and we're just checking to see are they viable, so we can use them. Okay, so just to run over then, we use the Abtec biological sensitivity rings for them, and the Carolina were the suppliers. Carolina were the suppliers of the phage and of the E. coli, and that's where you get those. Okay, so I think they go in the incubator. They're in the incubator for 3 days at 35 degrees, and then after that you can photograph the plates. That's it for today. Thank you.